we don't have it. The shower there because it's kind of convoluted. You have to.
Okay, guys, can you hear me now?
Yes, we can hear you now.
I'm sorry. Why did you say that? I was not aware of it. I was just talking to myself, I guess. Anyway, did you guys know what I was talking about?
I saw your hand movements as if you were talking. I just wasn't sure if you were talking to us.
Yeah, sorry. Yeah, I was talking to you. Okay, so what I was actually recalling, so it wasn't really a big deal. F is onto. If given any element in the codomain, I can find an element in the domain that's mapped into it. And F is one-to-one if whenever the inputs are different, the output are different. Or equivalently, if the output are the same, then the input has to be the same, which are the contrapositive. Okay, so those are the basic definition. And then we define the composition of two functions. No, we say that F is bijective. Definition if F is one-to-one and onto. Okay, I'm just recalling definitions, so you guys haven't missed a lot. And then we define the composition of two functions. So we have a function from X to Y, and we have one from Y to Z. So that was the picture. I have a function F from X to Y. So this goes from here to here. And G, so this is my set X, this is my set Y, and this is my Z. And we define the composition G composed with F a new function, which is, of course, all of you know it, was defined as follow. You start with an x. You ask yourself, what does f2 do it? And once you know what f2 do it, you ask yourself what g does to it. And that's really the composition. Okay. And what we proved last time, we proved the following. If f and g are both onto, then we compose them. The composition is onto. So that's what we stopped last time. And today we're going to check that. We're going to prove the following. If f and g are 1-to-1, then when you compose them, you're going to get also a 1-to-1 function. Okay, so let's do that now. That's the new thing. So let me get a new paper. So fact or theorem, and I don't use much the word theorem in this class, but you can state it like that. So if f is a function from x to y, and g from y to z. Sorry, I meant to z. So if f and g are 1-to-1, then their composition, I have to be careful how the composition here is g composed with f. That makes sense because f of x is in y, and then g of something, then g composed with f is 1-to-1. All right. So how do we show? Let's see how does it work. And here I start wanting your help. What does it mean to be 1-to-1? It means that I start with 2 input values. 1-to-1 means if the output are the same, the input had to be the same. Or if the output is different, then the input has to be different. So to show 1-to-1, we can actually use either one of them. And most of the time, or last time I told you, this is usually easier to use. Okay, so we're going to use this property to show that the composition is 1-to-1. So how we going to do that? This is my x, and this is my y, and this is my z. So the composition now is a function. Its domain is x, and its codomain is z. That's where my function is. And when I show it's 1-to-1, means I have to take any 2 values in the domain, x and x prime. So let x and x prime be element in x, such that they have the same output. It means g composed with f is g composed with f prime. Okay, so that's what we have. Let's take 2 elements such that g of the first is g of the second. It means when we compose them from here to here, what I have is g of f of x is the same as g of f of x prime. And my goal is to show you that if this is the case, right here, I have to convince you, this is the case, then x and x prime are equal. Okay, so that's how we show 1-to-1. So we take 2 points in the domain such that the output is the same. You have to convince me using my hypothesis. That's my hypothesis here. And that's my conclusion. You have to convince me that x and x prime have to be the same. Okay, and as usual, I will give you a little bit of time, like a minute or so, to interact with the problem. Why? How can I go from here to here? How can I go from here all the way to here using my hypothesis, everything I have? Okay, think a little bit about it and then we talk, but I want you to think about it. So just think, how does the composition work? And how can I use every bit of a hypothesis I have? Anybody has any idea, just say it. Anybody?
So,
I'm listening.
so we know that F is 1-to-1 and G is 1-to-1. And if
Yes,
you
given.
take
Yes.
F and you have X, so F of X is equal to F of X prime, and
On what
then
basis?
that we know F is 1-to-1.
Yes.
So F of X equals F of X prime, then we know X is equal to X prime.
We don't know that. We have to prove this.
Uh,
What do we know?
My idea is because the G is 1-to-1, that's why I have the F of X equal to F of the X prime.
Okay, what we have is this. That's the only thing I have. I
Yep.
do not have X equal X prime. You
Yes.
have to convince me X equal X prime. Is that,
Yeah.
are you with me?
Yes, but because of that equation, the G compose F of X equal to the G compose F.
That's a
of
crucial
X.
step. That's a crucial step. You cannot go here unless you mention that. So let us see what Kai is saying. He's telling me, okay, G composed with F of X is equal to that. It means that by definition of composition, so the definition of composition of function, definition of composition, it means G of F of X equal G of F of X prime. That's how the composition makes sense, because that's what G composed with F. So in the picture, this is my F of X, and this is my F of X prime. That's how I see it in the picture. But I know that F of X is equal to G of X prime. But because G is 1-to-1, it means those have to be the same. Okay, but G is 1-to-1. That's crucial. Hence, if G is 1-to-1, it means F of X has to be equal to F of X prime. Hence, F of X is equal to F of X prime. I can't assume F of X equal F of X prime just like that. The only reason I have them equal because G is 1-to-1. Since G is 1-to-1, it means they are both sent, F of X and F of X prime are sent to the same number, because that's what definition of composition. It means now those have to be equal. Now I can use the argument that, but now since F is 1-to-1, it means those has to be equal. So I'm going backward, as you realize. That's how I'm thinking. Since F is 1-to-1, then I can conclude X equal X prime. Okay, so every step is needed. I definitely need a G 1-to-1. Without G 1-to-1, actually, this is false. Without F 1-to-1, this is not true. So I need both of them to be 1-to-1 to be able to conclude that the composition is a 1-to-1 function. Okay.
so because we know G is 1-to-1, we're treating F of X like an input of G.
Absolutely.
So we know the inputs are
Absolutely.
equal. So
Absolutely.
it's essentially just a Y.
What?
It's like just a part of Y at
Exactly.
that point. Okay.
Exactly. It's the Y. That's the input. Absolutely. That's the input of G. If you want to use this language, which I don't care if it's fine with me. Sorry. So I'm using F of X as the input. All right. Any other questions? Very good. All right. I'm going to do the same problem, but instead of using this definition of 1-to-1, I'm I'm going to use the other one. Usually I don't use it a lot, but I think it's actually kind of nice in this problem to use both of them. So I'm going to redo the problem, but I'm going to use the second definition, okay, because I find it nice in this problem. So we're going to do the problem again. So now we're done. Now I'm going to show. We're going to do the problem again using the equivalent definition of one-to-one. Of one-to-one. Okay, so let's see what's the equivalent definition. I'm going to set it up. The picture is the same. So G composed with F is from X to Z. Okay, I want to show this is one-to-one using the equivalent definition. It means I have to start with two elements in the domain such that X different from X prime means I want the input to be the same, and I have to convince you. So from here to here, that's really how I want you to help me, that the output under G composed with F has to be different than G composed with F of X prime. Okay, so that's, I want to do it in a different way. I want to start with X different from X prime. And you have to convince me that G composed with F has to be different than G composed with X prime. So I just draw a little bit here because it helps me. I hope it helps you also. So this is my F, this is my X, this is my Y, and this is my Z. I have X, and X prime, which are different from each other. And you have to convince me somehow they have to be mapped to two different numbers. Okay, so that's another. I'm doing the same problem in two different ways by using the two equivalent definition of one-to-one. Okay, get going. Almost every one of you can think through that. I don't think this is a very hard one.
So we know the G is the one-to-one and F is one-to-one, right?
Yes, absolutely. It's the same problem.
So because of F is one-to-one, so F of X equal to F of X prime.
Watch it. F of X is what?
Not equal.
Not equal.
Not equal, exactly. Because if this is, this is sent to F of, what?
No, I forgot that is a new questions.
Mm-hmm. And so that's the same question, but we're doing it in a different way. Are you with me?
Yep.
Yeah. So I'm assuming those are different, and I want to show that under G composed with F, the output will be different. I'm doing the same thing basically, but I want for the first time use both definition to it's good. So if X is different from X prime, because F is one-to-one, those have to be different from each other. So X is different. Since F is one-to-one, it's crucial, I need it. Means the output under F has to be different from each other. Okay. Keep going. You guys are fine. Keep going. So that's my F here. I use the fact that F is one-to-one. It guarantees that F of X prime are different.
Since G is one-to-one.
Now, since G is one-to-one,
G of F of X.
Now I'm using F of X as the input of G.
Is not equal to G of the F of X prime.
Okay, now I'm using that. Okay, G is here. It's going to send this to F of X. And this is going to send to a totally different one because G itself is one-to-one. But now, by definition of composition, so that's what the composition, G of F is basically, that's what G composed with F is. That's really the definition of composition. Is different than G composed with F of X prime. Okay, and of the problem. So we did this problem in two different ways. One, by assuming the input are different, showing the output has to be different. And the first approach was assume the output are the same, and we went backward. And I showed you then the input will have to be the same. Okay, so for Tuesday, I will assign other problems along the same line. I mean, for Wednesday, and we discuss them in class. So now we have the following. So the composition of two. So now we have the following theorem. Suppose F from X to Y and G from Y to Z. If F and G are bijective, remember, bijective means one-to-one and onto. Bijective means, this is the picture for bijective. That's the picture. It means if each element is assigned one element, one element, one element, and every element in the codomain is assigned to something. So that's a bijection, sometimes called one-to-one correspondence. That's the picture for bijection. There is no extra term here because we want to make sure onto is satisfied, and no two element is sent to the same one because we're going to guarantee the one-to-oneness. So if F and G are bijective, then their composition is also bijective. Now we're going to talk a little bit about the inverse of a function, and then we talk about the cardinality, which is the last idea in this course. So the inverse of a function. You know it. I know you know it back from probably junior high or wherever, but we're going to talk about it a little bit deeper now. So the inverse of a function. Suppose F from X to Y be a bijection. Important. It means one-to-one and onto. Okay, so the picture is, this one is the picture. X to Y. This is my F. And let us say we have 4 elements. Later on, I will take infinitely many, and suppose this goes, we're going to call 1, 2, 3, 4, A, B, C, D. So I'm going to send 3 to D, and I'm going to send this one here. That's a bijection. That's a one-to-one and onto. Then the inverse of F. The inverse of F is going to be a function. That's the inverse. From Y to X. That's the inverse. So it's going to go from Y all the way to X. And basically, it's going to undo what F does. So this is A, B, C, D, and 1, 2, 3, 4. F inverse is going to do undo. So if F send 1 to A, F inverse will take A back to where it comes from. If F send 2 to B, F inverse again will send B to where it came from. F send 3 to D, the F inverse will send D back to where it came from, and it sends C back to where it came from. It totally undo whatever F is doing. So the output go back to their input. So now the inverse of F denoted by F inverse, that you guys know very well, is defined as follows. Is the function from Y back to X. So it's a function Y back to X. that does the following, and is defined by F inverse of y is the unique element, of x, which is in x, such that f of x equal to y. So f inverse of y is the unique element of x, so the unique element x of x, sorry, such that f of x equal to y. So now 2 questions before we proceed. Do we need f to be 1-to-1 for f inverse to make sense? Question number 1, do we need f onto for f inverse to make sense? So for the first question, if f is not onto, does f inverse make sense? Back to you now. Suppose f is not onto. Can I define f inverse? What do you think? Yes, no? What will be the problem? I mean, because why am I putting this restriction on f? Why I said I want a bijection. Suppose f is not onto. Will f inverse be a function? Yes or no?
No,
Because
f is not onto.
how this is affecting? What's the picture? What happened in the picture? That's gonna make this a problem.
Wouldn't it be because if like one of the variables like is left out, so say if you have 4 and then the first 3 hits, but D is left out, wouldn't that mean it's not 1-2?
Right, suppose I have 1, 2, 3, and this is F, and D, and F is 1-to-1. Okay, that's my X, and that's my Y. So F inverse will not be a function from Y to X, because remember, definition of a function, it means that to each element, so F inverse is gonna go from here to here. That's what F inverse here. So, but the definition of a function, it means to each element in the domain. So the domain of F inverse, okay. F inverse will be a function from Y to X. So the domain of F inverse is gonna be the codomain of F. But here, if this is the domain of F inverse, D is not sent to anything. So F inverse cannot be a function, because by definition, F is a function from Y to X if to each element of Y, we can associate an element in X. If the original function is not onto, I cannot send anything to D. It means F inverse is not defined. Okay, because question is, F inverse of D will be what? It's not defined. Therefore, we don't have a function. Okay, so onto is important. And more important is 1-to-1. Suppose if, what?
So in the future, we can just use it, right?
What do you mean?
Like if the f is not onto, so the inverse of f is not
defined.
defined, we can just write it, right?
Exactly.
You
exactly.
don't have to write a graph and just show like why.
If you know it's not onto, yes, F inverse is not defined.
Okay.
Absolutely, absolutely. Unless you change the codomain. But we're not worried about that in this class. We take a more advanced class. Sometimes we can restrict the codomain to the range, but I'm not gonna talk about that in this class. Now, if F is not 1-to-1, F inverse is not defined. Why? Because conditions are not put for just because we like conditions. Why the 1-to-1 is absolutely necessary for the definition of F inverse. Back to you, work with the graph. How is F inverse defined? So I'm going to take a picture where this is my f, and my f failed to be 1-to-1. Then what's going to be the problem? So I draw a picture of me while you guys are thinking. So that's not 1-to-1. All right. So why it is absolutely necessary to have f not 1-to-1? Why f inverse is not defined? Now back to you.
If you reverse it, you'd fail to be a function then, because you'd have one output sending to multiple, or one input sending to multiple outputs.
Exactly.
Right?
The problem here, because look at A. That's why I draw the picture. I really want you to actually really see it. F inverse of A is not defined because the definition here, watch carefully how I define the F inverse, is the unique element. What allows me to say unique element of X is the one-to-oneness. That's really what allows us. The unique element X of X such that f of X equal to Y. Why I can write unique? Because my function is a one-to-one function. So if I take any element here, that is a unique element which is mapped into it. That's the one-to-one unique. I don't have two mapped into it. So it's absolutely crucial to have a one-to-one function. So here f not one-to-one, so f inverse of A definitely not defined. Because where the function has to be absolutely not ambiguous. When you define a function, there should be no ambiguity in how you define it. If two things, one and two go to A, f inverse is going to send A back somewhere. Where is going to send it? There is nowhere else. So the idea of f inverse, a function has an inverse if two conditions are satisfied. If it is one-to-one and it is onto. Otherwise, we cannot talk really about the inverse of a function. Okay? So before I take two examples where we're going to compute the inverse, I actually would like to take you back to calculus 1 or wherever we see this stuff. No, actually pre-calculus. Okay, so then I take example and we find f inverse. But I would like to talk about this. Suppose, back in, not pre-calculus, in the trigonometry class. Suppose I take the function f of x equals sine x. Okay, so I'll take a nice piece of paper. That's better. F of x equals sine x. Okay, and this is the graph of the sine. That's the graph of the sine. So it's like this at 0, go up, down, and it keeps going forever. And then it goes up, down, and keeps going forever. So the input here is a real number, that's the sine function. And the output, and because if you remember, the sine function is always between -1 and 1. So I can say that this could be -1. Okay. Now question addressed to you. Does this function has an inverse? Does sine has an inverse as a function from R to -1, 1? Yes or no? Why you're silent? Does f inverse exist? So let's look at the graph. Is this function onto? Yes or no? Graphically, I don't want any proof. Is f onto? My codomain here is -1, 1. And as far as my codomain is concerned, is it onto? It means if I take anything between -1, 1, anything, can I find an input that's mapped into it? Yeah, I can always find an angle that maps into it. Is f onto 1?
You would have to restrict the domain if you want it.
Absolutely. Is it F 1-to-1? And the answer is no, definitely. The sign is not 1-to-1. And that's why what we do in calculus trigonometry, what we do is the following. We restrict the domain to minus pi over 2, pi over 2. We absolutely restrict the domain. And we define the inverse when the domain is minus pi over 2, pi over 2. In other words, when we take f of x by restricting my domain from minus pi over 2, pi over 2, all the way to minus 1, 1. So this is gone for me, and this is gone for me. So if I restrict myself here, this function is 1-to-1. Okay, or actually, where f of x is sine x, this is 1-to-1 onto, when I restrict my domain. So the sine inverse of x is actually become a function from minus 1, 1 all the way to minus pi over 2, pi over 2. So the sine inverse is a function. That's why when we teach trig, we tell you the sine inverse is the angle between minus pi over 2, pi over 2, whose sine is x. So sine inverse of an angle here is the angle between minus pi over 2 and pi over 2. We restrict the angle, otherwise this has no sense whatsoever. Otherwise the sine inverse will not be a function at all. So by restricting the domain here on the sine, I take the inverse from minus 1, 1 to minus pi over 2, pi over 2. And that's usually a lot of time idea that give us a lot of trouble when we teach trig to the student, to understand that the sine inverse gives you the angle here. It doesn't give you any other angle. Okay. All right, so that's a small comment. Now we go back to our problem. So we're gonna do two problems, a simple one and one's not also hard. So the first one, suppose I take the function f of x equal x cubed plus 1, and I want this function from R to R. Okay, and question number 1 is show f 1-to-1. And question number 2, show f onto. And question number 3, find a formula for f inverse. Okay, take you back absolutely to pre-calculus where you've done this stuff. But now we have to make sure that our conditions are satisfied. So my domain is R, my codomain is R. So we have to be very careful with domain and codomain. Show f is 1-to-1. Okay, it means let x prime be in R such that f of x equal to f of x prime. And I want to conclude x equal x prime. So that's really simple. It means x cubed plus 1 equal to that. So we set the output equal. It means x cubed equal that. I take the cubic root, x equal x prime. 1-to-1 is easy. Now show us f is onto. F onto, as I did last time, and I'm going to do another one, I always do my scratch because onto. Onto, it means we're moving backward. It means we're basically doing this piece here. We're doing backward. So I'm going to take y in R. So we say let y in R. And I'm going to find x such that f of x is equal to 1. So that's a simple scenario. I can just solve for it. I don't have to guess or anything like that, like the previous problem. So I'm going to let y be in R, take x to be the cubic root of y minus 1. Okay, and then f of x equal. You have to make sure that my f of x is y plus 1. I have to verify. This is equal y minus 1 plus 1 equal to 1. So that's f is onto. It means my function f inverse exists. We know that it satisfies both property. Now find a formula for f inverse. So now what's the formula for f inverse? F inverse is nothing more than the function that goes backward. It means if I know the output, F inverse is what is the input that's coming from. But I've already constructed the input. So F inverse of y, if I start with an output y, F inverse of y is nothing more than the cubic root of y minus 1. So when I actually show that it's onto, granting it's 1-to-1, when I show it's onto, I'm actually finding immediately the F formula for F inverse. So that's what F inverse is. So we start with an output here. We know what the input. Okay. All right. We're going to do another problems along those lines, and then we proceed to the idea of cardinality. So another one, which is one of you asked me about last time. I'm going to make it now. So let F be a following function.
Professor,
I'm listening.
can you repeat the third part again? Formula for the inverse.
This piece.
Yeah.
Okay. What does it mean to find a formula for F inverse? Okay. Let me clarify it. So now F inverse is going to be also from R to R, right?
Yeah.
Yeah. And this is my F. So F does the following. Take X to X cubed plus 1. Okay. What is F? What does it mean to find F inverse? It means the following. A formula for F inverse. It means you have to go backward. It means if you know Y, you know the output. Can you give me the input that will bring up this output? That's what it means to find a formula for F inverse. It means if I know my output here, I call it Y. Finding F inverse, it means finding the input that will go back to Y. Because what is F inverse of Y? F inverse of Y is the X such that F of X equal to Y. So finding a formula for F inverse means if I know the output, what's the formula that will give you the input immediately? So I'm going to start from here. So we're going to start with Y in R. And the question is, we need to find the X such that F of X equal to Y. Now, by showing onto, we realize that this X is the cubic root of Y minus 1. It means what does F inverse do? Whatever you give it, the output is gonna be the cubic root of Y minus 1. Okay. You follow anything?
Yeah.
Okay, are you sure? All right, so with this in mind, let me go back to this problem. Let that be a function from R to R, from the Cartesian product to this, okay? And it's defined as follows. Remember here, the input is in ordered pair. My output is in ordered pair. So I'm gonna send it to m minus n, m prime plus n prime. That's what I want. M minus m, oh, I'm sorry. Okay, and m plus n, okay? Question number 1 is that show F1 to 1. All right, what does it mean? We have to take 2 pairs. Let mn, 2 pairs, such that their output is the same. That's what we show 1 to 1. We take 2 ordered pairs that have the same output. And we have to prove that the input are the same. If the output are the same, we have to prove the input are the same. All right, so let us set equal. F of mn equal to that. It means m minus n, m plus n, very simple, equal to m prime plus n prime plus this. Okay, but what does this mean? If this pair equal to that, it means the first entry here should be equal to the first entry here. And this entry here should be equal to this entry here. Okay.
How does, for m prime plus n prime, how does it, isn't it supposed to be m prime minus n prime?
Okay, thank you very much. You're right. How can I get to here? Help me out. I have this entry equal to that, and this equal to this. How can I go from here to here? Okay, I know one of you asked me this question last time, so I incorporate it as a problem. There are different ways. There is one way that jumped to my eyes. Let me see if it will jump to yours also. Basically, you have two equations. I mean, we have 4 unknowns, but we have basically two equations. And I want to conclude if this hold and this hold, then m has to be equal to m prime. Because I told you it is 1-to-1, so I told you that. Any ideas? One approach, add them. What do we get? If this hold and this hold, if we add them, what do we get? Minus n plus n cancel each other. We get 2m. Add them equal to m prime. Means m equal to m prime. So one way you can do it just by really adding them. Now, since m equal m prime, now I can add m plus n equal m prime plus n prime. It means that I can substitute this for m. They are equal, means n equal n prime. So m equal m prime, n equal m prime. So we have the ordered pair mn equal to the ordered pair m prime, n prime. And so that's how we're going to show 1-to-1 when we are dealing with Cartesian product. Now, question number 2 is that show that f is onto, and then find a formula for f inverse. So show that f is onto. Again, I write this f. My f is, I rewrite it because I R cross R, and it takes the input mn to m minus n, m plus n. Now I want to show it something. What does it mean? It means I have to start from something in here. I'm going to give it a name. And I'm going to find what is the pair that's mapped into CD. That's really how to show onto. Means you have to give me that you can find a pair that's mapped into CD. And that's where my scratch starts. So here we say, okay, let's start with something in the codomain. I can call it CD, you can call it anything under the sun. I don't really care what you call that ordered pair, R cross R. And we have to show that I can find Mn such that f of Mn equal to CD. Okay, so I'm going to start with something here. I'm going to find something in here which is mapped into it. So in this problem, CD is given to me. So CD is what I know. And I need to find Mn. I have to find Mn such that f of Mn equal to CD. So that's really what I want. Once I find them, if I can, then I go back and write the nice stuff in here. All right, so what do I mean? F of Mn, it means I want m minus n m plus n to be equal to CD. Remember, m and n has to be in terms of CD because that's what's given to you. And everything I have to find should be in terms of the only thing given to us. All right, so if this occurs, it means m minus n equal to C, m plus n should be equal to D. Now I need m and n in terms of C and D. Okay, so now of course, if we look at that, C and D are the known, m and n are the unknown. C and D are known, and n are the unknown, and I have to solve them in terms of C and D. So you can use anything you want. You can even use linear algebra at this stage, but not necessarily. If we add those two equations, so basically I'm solving. I have a system of two equations. The unknowns are mn. I have to solve them in terms of C and D. So we can solve them very easily. If we add them, in this case, we can use the elimination method. I will get 2m equal C plus D, which will give me m equal C plus D over 2. So if I have CD, I can find my m. Now, is it in my domain? Is m? Yeah, m. Because I put R, I am safe. If I had put Z, m may not be in my domain, and the function may fail to be onto. But this time, I want it onto. So this is my m. Now I need n. Okay, you can use any equation you want to get your n. So let n is, I use this one, it's m minus C. It means C plus D over 2 minus C. So I would get D minus C over 2. So now everything seems to be fine. Giving any CD, I was able to find m and n in my domain. So now I write the proof. Let CD be in R. Take m to be C plus D over 2 and n to be D minus D over 2. And then I have to convince you one more time that f of mn is equal to CD. So that's really how we prove. We do the scratch, we do everything on the side, and then we say, you know, that's my m, that's my n. Let me make sure that this mn is sent to CD. So f of mn is equal to that, equal to. I have to convince you at the end that my choice is a good choice. My choice does go to CD. Okay, so now I plug him back in. What does f do? It takes away the minus. That's what it does. And then it takes C plus T over 2 and add D minus D over 2. Okay. And the question is this CD. Okay, C, so I'm ending up with C plus D minus D plus C over 2, which is definitely a C. And this I'm getting C plus D minus C over 2, which is absolutely equal to CD. So my function is absolutely an onto function. Okay, so you give me anything. So if you give me anything here, you give me like 2 and 15 here, anything in here, suppose if you give me 2 and 15, I can tell you where this is coming from. That's really what I am doing. You give me 215, I tell you where this is coming from. The m is the sum divided by 2. That's where it's going to come from. The n is the difference, 15 minus 2. 13 over 2. So you give me anything here, I know where it comes from. If I take this, find f of that, I will get 215. That's really what we're doing. You give me anything here, I can give you where it comes from in general. So I basically gave you a formula for that. And now the question is, so f is 1 to 1, f is onto, find a formula for f inverse. So f inverse in this case is a function from R cross R into R cross R. And what does it mean? Find a formula for it. It means, again, if you know the output, what should be the input that's going to be sent into it? So the formula is going to be F inverse of CD is equal to, we pick it up from there. We already found it. C plus D over 2, D minus C over 2. F inverse of CD is the input which is sent to CD. That's what F inverse is. Which input is sent? I need a formula for it. Which input is sent to CD? This is the input which will be sent to CD. And that's the general formula for F inverse. Okay, please ask questions before we move on. One property of F inverse that we definitely have to talk about, which is the following. And you guys will give me the answer. So first, I'm going to talk about the identity function. Okay. Identity function. Suppose A is a set or X is a set. Let X be a set. Then I, which will stand the identity, with an X here, is the function from X to X given by I X of X equal to X. Ix is called the identity function. Identity function. Okay, so it's the function that take X into X. And that's really the notation. Ix, it means the function that take X to X. And now a very simple theorem. Okay. Which is, I think you should be comfortable with. Suppose F is a function from X to Y. It's a bijection. 1-to-1 onto. And so it has the inverse. Bijection. Then, okay, you have to answer my question. If I take F inverse and I compose it with F, what should I get? So that's a composition. So F is from X to Y, inverse from Y to X. If I take F inverse composed with F, what those will give me? So suppose F.
That would just be the identity because you're
This will be
sending
exactly
X
the
to X.
identity. That will be the identity. Because I suppose F sends X to Y. What's the job of F inverse?
To send it back.
To undo it. Send it back to X. It's exactly what F inverse does. Whatever F do, F inverse is gonna basically undo it. So if X in general, like all the pictures I gave you, if F send 1 to 2, F inverse is gonna send it back to 1. So F inverse composed with F is gonna be the identity X. Now, what about F composed with F inverse? Is it the same idea? Okay, what's F composed with F inverse? Anybody? So suppose F inverse,
Would you have
take
the
Y
identity
to
of
X.
Y?
What will F do? Take X back into Y. That's really what it does. But what's the identity?
The identity of Y.
That should be the identity of Y. you have to be very careful because f inverse, the picture here, f inverse is from y to x. That's f inverse. F is from x to y. So f composed with f inverse is going to be a function from y to y. And it is the identity because for exactly the same reason. If f inverse is sending y to x, so this is f inverse of y, f, so that's f inverse. The job of f is going to take x back into y. Okay, so f inverse composed with f is the identity on x, and f composed with f inverse is the identity on y. Okay, that's very important property of the inverse of a function. Okay, so the inverse of a function is defined as long as my function is a bijection. So if a function is one-to-one onto, then we can construct its inverse, then we can move backward. And to find a formula for it, which is, it's basically it means that if you know the output, finding a formula, it means finding the y, give me a formula that will give you the x. So finding a formula is the same thing basically as showing it is onto. That's really how we get the formula. Once I show it's onto, basically I get the formula for free. But main restriction is we have a one-to-oneness. Otherwise, the whole thing makes no sense whatsoever. All right, this, in a way, this idea of bijection would lead us to the last idea I would like to talk about, start today, is the notion of cardinality of a set. Now, we've talked about cardinality, but we're going to talk a little bit more about it today. So, what's the cardinality of a set? Cardinality. Let's remember, let X be a finite set. Set A is called finite. Is called finite if it has finitely many elements. So 5 elements, 6 elements, 100 elements, 1,000,000 elements, but finitely many elements. And otherwise it's called infinite. Like n, z, all those are infinite. Now, if A is finite, it's finite, so it's a set, collection of objects, then the cardinality of A is the number of elements. Which is denoted like this, is the number of elements of A. Okay. Now I'm going to state some simple facts that you're going to help me with it, but it's going to motivate, a kind of a general definition of cardinality. So, simple fact. Suppose X and Y finite. Finite set. They have finitely many elements, and that's important for now. Finite set. And f a function. So we have a certain function from X to Y. So they are finite, and I have a function from X to Y. Suppose f is one-to-one. Okay, so suppose I have a function one-to-one. Then what can we say about the cardinality of X and the cardinality of Y? I want you to think.
They're equal?
No.
No.
Why no? If it's one-to-one, one-to-one, only one-to-one. It's from X to Y. And it's my F. 1, 2, 3, 4, 1.
Oh,
2,
you'd have to say that Y is greater than or equal to?
Right. If it's one-to-one.
It's not necessarily equal.
yeah, if it's 1 to 1, then the number of element in X is less or equal to the number of element in Y. Does this make any sense? As long as it's finite. Because we have this correspond. Now, Y can have more element. We know that because it's not necessarily onto, but how many element in X is always less than how many element in Y, because we have this 1-to-1 correspondence. So if I have 4 here and they are different, they're going to be assigned to 4 different element in Y. So Y should have at least 4 different elements, but it can have way more because it's not onto. So if F is 1-to-1, then the cardinality of X is less than the cardinality of Y. Suppose F is onto. Then what can we say about the cardinality of X versus Y? So this is the 1-to-1 picture. Now the onto picture. So this is X and this is Y.
You would know that X is greater than or equal to Y because everything in Y is hit, but
Right.
multiple elements of X can be hitting the same. of Y.
Exactly. So this are, let us say F has 4 elements. Each one of them has to come at least from 1. It can come from 2, but at least from 1. 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 So X should have more element than 1. The cardinality of X is bigger than cardinality of Y. Now, suppose F is a bijection. Again, I'm working with finite set. All my arguments don't work if I don't have finite set. Suppose F is a function from X to Y. Suppose F is bijective. Then what can we say about the cardinalities of X and Y? Bijective, the picture is this 1-to-1 correspondence and 1-to-1 and onto. So
Now
every
they're equal.
element here has to go to exactly 1. Every element has to go to exactly 1. And every element here has to be hit. So if this has to be the case, then the set should have the same number of elements. So if F is a bijection from X to Y, X and Y are finite, then X and Y have the same cardinality because there is this 1-to-1 onto correspondence between them. Okay, so if X and Y are finite, so if X and Y are finite set, and F from X to Y, so we can find a bijection and we can find F from X to Y bijective, then the cardinality of X is equal to the cardinality of Y. So if 2 sets are finite, if we can find a bijection between them, then they must have the same cardinality. And this is going to motivate the following definition, which is not trivial. I mean, the definition is easy, but it's actually very interesting. This is going to motivate the following definition. So we're using this as a motivation. Let X and Y be 2 sets, not necessarily finite anymore. Be 2 sets. I didn't say finite. X and Y could be infinite. Then we say that, and that's a definition now, that X and Y have the same cardinality if we can find if we can find a function f from x to y that is 1-to-1 and onto. Now I am giving you a definition, 1-to-1 and onto. Okay, so now that's the definition. If the sets are finite and we can find a bijection, then naturally the cardinality is the same. Okay, because this 1-to-1 onto correspondence. Now, if two sets are infinite, now a definition, we say that they have the same cardinality if we can find a function from x to y that is 1-to-1 and onto. That's what it means the same. So we can have this 1-to-1 correspondence. Everything in x will correspond to a unique element in y. And everything in y is coming from an element in x. Okay, so let me ask you the following questions. So now, example. Let E be the set of all even numbers. So let's see the set of all actually even numbers. And is even. So 0, plus or minus 2, plus or minus 4, and so on and so forth. Question is, show that E and Z have the same cardinality. Okay, so E, all the even number. And you want to show that they have the same cardinality. What does this mean? You know, E is only the even, Z everything. I want to show that they have the same cardinality. What does it mean? It means you have to find a bijection that go from one to another. So I want you to construct, I want you to find a function f from Z to E, which is 1-to-1 and onto. So I like sometimes to draw pictures, 0, 1, 2, 3, that's my Z. That's Z. And my E is here, 0, 2, 4, 6, minus 2, minus 4, etc. And I want you to find a 1-to-1 onto 1. We can think of a function which is 1-to-1 onto from Z. I mean, of course, we think that Z have a lot more elements, but I'm telling you no, actually they have the same cardinality. What's the most natural function you can think of from Z to E?
So if n's in Z, you just say 2n?
2n. Is it 1-to-1? Is it onto? Question number 1, is it defined? Take any n in Z, the output to n is definitely an element of E because 2n is even. So well defined. Question number 2, f1-to-1. Because that's simple. Suppose I take two elements such that if f of n equal f of n prime, then n to n equal to n prime, it means n equal to n prime. Check. Last question. Is F onto? So it's well defined because it telling me 2n, I have to make sure that 2n is in E because this is not Z, it's E, or the even number. So it is well defined because my output is an even number. Now the question, is it onto? It means if I take any element in here, can you give me the element in Z that's mapped into it? Yes or no? And you want to write a good proof, a good little proof. So what are you guys doing? What's his function? Send 0 to 0, 1 to 2, 2 to 4, 3 to 6. That's really the function that we are constructing. And now my question is, can you reverse it? And what's going to be the reverse formula? If I take anything in here, is it coming from somewhere?
You just have m over 2.
Okay, so we're going to start with an element in E, right? Be an element in E. What does it mean? What is E? E or the even? It means Y is equal to N for some N in Z. They are very, very particular element. So let's take X to be N. Then f of X is equal to 2N is equal to 1. Okay, so we start with Y in E. And basically what I'm taking X to be is what I'm taking X to be is Y over 2. But the question is why I can take X to be Y over 2. I can take X to be Y over 2 because X is an even number. So Y over 2 is an integer. Actually, this will be easy for us. Let X to be Y over 2, that's an integer. Then f of X is equal 2 times Y over 2, which is equal to 1. Okay, so I repeat because I scratched and I don't like that. So I repeat exactly. So let me take Y in E to F onto. Let Y be in E. And I'm going to take X to be Y over 2. And we're going to note that X is in Z because Y is even. So Y over 2 is an integer. Otherwise, I cannot take Y over 2. And f of X is actually 2 times Y over 2, which is equal to 1. So Z and N, Z and E have the same cardinality. Okay, because I was able to find a bijection between Z and E. Okay, even though it seems to us that E has less element than Z because we're missing all those 2s and 4s and stuff, but the idea, no, they don't have more element. They actually have the same cardinality because I can build this one-to-one onto correspondence between them. Okay. All right, I definitely have to stop here. You guys probably didn't hear me at the beginning, but your exam is next Monday because that's the scheduled time. There isn't much I can do about that. And so the final exam. Okay, and I think I put on Brightspace. The scheduled time is from 12:30 to 2:30. That's the scheduled time by the university, but I'm not gonna stick to that time. So I will open the test at 12:30 and I'm gonna do like the exam one, I will close it at 11 p.m. So you will have, I don't know, 11 hours to do that. Okay, so I will open it at 12:30 p.m. I will close at 11 p.m. The final is going to be comprehensive, so it's everything that you guys have done so far. On Brightspace, I have all the subjects that you are responsible for. So the best way for you to review is actually, as far as you guys are concerned, is go over your homework. And I have solution to most of them, and I will be finishing up this week the solution to everything. And if any student have any problem with this time, please let me know now. I try to give a big range so everybody can fit into this range.
So the final exam this time will be timed, and we can open it and it'll close whenever.
It closes at 11 p.m.
Okay, but like, what I guess my question is like, do we turn it in within a certain amount of time after we open it, or we just have from 12:30 to 11 to 5?
You have all this time,
Okay.
like the first exam.
All right. Cool.
Okay. All right. You
Yeah.
guys have plenty of time, just like the first exam. I'm not limiting you, so nobody should have any issue, basically. I mean, you have all the time you need. All right. So this is the time frame. It will be comprehensive. Everything you guys will be responsible for. And for Wednesday, I'm going to assign some practice problem, but please do them because I don't want to give you homework on functions because you guys have a lot by now, a lot of homeworks in other classes, but I'm going to assign practice problems for Wednesday. I want you to do them and we will discuss them on Wednesday instead of giving you a written homework. Is that clear? You hear me?
Yeah.
So what did I say?
Practice problems for Wednesday. Just
Do
do
them.
them.
Okay, and then we can discuss them. And I will discuss any other questions you have, and I will address some of the mistakes that I see in your exam, in your homework. Okay, any questions? All right, I know that some of you show up on my office hours. Today, I will not have office hours because I have a medical thing to take care of. So those who have questions about the homework and they were planning to come to see me today, you can hand in the homework tomorrow and come to see me during my office hours tomorrow morning between 11 and 12. Okay, because some students do come and ask me questions. I have a medical thing and I cannot make the office hours. All right. Okay, bye-bye, guys.
Cool.
See you.
So you cannot make the office hour today?
Yeah, I can, no office hours today.
No office hour today, okay.
No, I have a medical, I'm still dealing with medical issues. So I
Okay,
have a
no.
doctor's appointment. I couldn't.
We can submit our homework tomorrow, right?
If you want to, yeah. If you have questions and you want to ask me, you can submit them tomorrow. Absolutely so.
Yeah. So can I see the final exam again, the time?
It's on Brightspace. It's on Brightspace.
Okay.
Everything is on Brightspace.
Okay,
All
thank
right?
you.
Okay, any other questions? Okay, bye-bye, guys. See you on Wednesday.